My name is Shivan Bissesar. I'm a master's student of applied physics from the University of Twente. Today I will talk about the research which I did during my internship at the University of Amsterdam. I will talk about spin-orbit coupling in orthogonal charge transfer states, and I will start by showing you some of the results which I like the most. Here we see the matrix element for spin-orbit coupling in wave numbers, as well as the electronic coupling which facilitates charge separation for molecular electron donor acceptor system containing pyrene and dimethylaniline. The squared quantities here are proportional to the rates of charge recombination and charge separation. These are plotted as function of the dihedral angle between the two units of pyrene and dimethylaniline. What this graph essentially shows is that optimal charge separation occurs at a dihedral angle of approximately 180 degrees. Triplet formation by charge recombination, however, is optimal at a dihedral angle of approximately 90 degrees. This opposing behavior is in line with the current scientific paradigms, but to my knowledge, this behavior has neither been determined with computational chemistry nor experimentally. I believe this substantially clarifies the spin-orbit charge transfer intersystem crossing mechanism. I have made use of time-dependent density function theory with the Amsterdam density functional ADF program to determine these properties. First of all, you may ask, why did I study charge separation and triplet charge recombination? Triplets in general have several applications. They can serve as photoinitiators for photopolymerization. They can be used in organic light-emitting diodes, which make use of thermally activated delayed fluorescence to increase the fluorescence quantum yield. Furthermore, they can be used for photodynamic anti-cancer and chemotherapy. They can also be applied in singlet fission for photovoltaic applications to surpass the Quasar-Shockley limit, which is the maximum theoretical solar cell efficiency. The molecular electron donor acceptor system which I studied during my internship was pyrene dimethylaniline. The reason I studied this molecule is that there's a lot known about this relatively simple molecule. Here, for example, we have some measured rates of triplet charge recombination in different solvents. We observe that this is one of the molecules in which charge recombination can occur very rapidly in n-hexane, that's within 40 picoseconds. What we also observe is that this rate substantially depends on the solvent which is being used. We would like to quantitatively understand this behavior and use it to determine the optimal conditions for charge separation and triplet charge recombination. To clarify this behavior, we make use of the classical Marcus theory. The first step here was to benchmark the method being used for determining a spin-orbit coupling. I have calculated the spin-orbit coupling for acetone and for thiothymine using different exchange correlation functionals with a TZP basis at the optimized S1 geometry. The values of the spin-orbit coupling match the values in literature. This essentially tells us that the method which we are using to determine the spin-orbit coupling is the correct procedure. In the next step, we calculate the excitation energies of pyrene dimethylaniline. From the excitation energies, we can determine that the S2 in this system forms the local excited singlet state. Pyrene here is the acceptor, and the dimethylaniline forms the donor. From the local excited state, charge separation occurs between the donor and acceptor to the singlet charge transfer state S1, and from this singlet charge transfer state, charge recombination can occur to form the triplet state T1. What this essentially tells us that when we're going to calculate the electronic coupling has to be calculated at the S2 geometry, while the spin-orbit coupling for charge recombination has to be calculated at the S1 geometry. I have optimized the geometries of pyrene dimethylaniline in different solvents, namely in a gas phase, in hexane, and in acetonitrile. Over here, we see the optimized geometries of pyrene dimethylaniline in hexane. Here we observe that the optimized states form a waving hand structure, which I find quite an intriguing result.